Okay, so in this other lecture, we're gonna I'm gonna teach you some important concepts, for example, diffusion times and the diffusion equation with decay. Also diffusion into tissue. And before I continue, guys, remember that we are recording and streaming on YouTube this lecture. Okay. We will also see how diffusion happens in membranes, in which you have different cells with different diffusion coefficients. Also, we will change this diffusion coefficient and see what happens when you put sources and sinks and decay and sources at the same time in the diffusion equation. So diffusion time, what is the diffusion time? The diffusion time is basically the time it takes for a particle to move a certain length in average, okay? Always remember, in average, because it's random. So time here is proportional to the square of the length. So because of that, diffusion is mostly relevant over short distances. That's why you don't see the dye diffusing on the video that I showed you the last lecture. And because diffusion is driven by those collisions, you expect that for larger molecules and heavier molecules like DNA, you will have a lower diffusion coefficient. So here is 10 to the -4, while for potassium, which is a small particle, much smaller than DNA, it's just an atom. In water, so water is even softer, let's say, than yeast, you have a much higher diffusion coefficient, okay? For a typical protein inside the cell, the diffusion coefficient will vary around 100 micrometers square per second. So you will expect a protein to travel in the tens of micrometers distances, okay? And there's a nice estimation here. It will take 300 years for a protein to diffuse 1 meter in average. This is an exercise for you to do these kind of estimations. For example, let's say you are a typical protein inside a cell. Okay, this is a little bit comic exercise. So your diffusion coefficient is 100 micrometers square per second inside the cell you're in. Now you want to travel, let's say, from the nucleus to the surface, and your radius is the radius of the cell is 10 micrometers. So you want to travel 10 micrometers with a diffusion coefficient of 100 micrometers square per second, and there is no active transport available. How much time do you expect it will take to reach the membrane? So 100 micrometers square per second for diffusion coefficient, and you want to travel 10 micrometers. How much time will you take in average? Oh, yes, I was muted. Yes, no, I wasn't talking. Thank you, Cheryl. One second? What about the other people? What do you think? $6.2 approximately. Not sure. Okay. I will do the estimation for you guys in case you are wondering how it's done exactly. So the estimation is roughly this. So L squared over D. So if you have 10 micrometers, the diffusion coefficient is in micrometers, so we don't need to change any units here. So you just need to elevate the length to the square and divide by 100. Okay, so this is 1. And the second, which is in the units here, so you have micrometers square over second. This micrometer squared cuts with the micrometers here. So, okay, and the second goes up, so you have 1 second as a result. So it's 1 second, okay? You will take about 1 second to diffuse. So I'm still confused why it's squared, not cubed. Probably, let me, no, it should be cubed. It should be cubed for 3D, for the 3D case. I forgot it when I was.
No, it's not. It's square, always.
Ah, yes, it's square.
Dimensional
I'm
analysis.
tripping. Yes, because the diffusion equation is always this. So yes, it's always the square. Sorry, I was tripping. No, it's not assuming 2D. James is correct. Of course. It's always squared. Yes. So you would need to have a different equation for it to be cubed. So it's not cubed, it's squared. Yes. So I don't know if I was clear for you, Sharon and Ajay. The diffusion equation is derivative on time, and you have a second derivative in the x, for example, in the spatial coordinates. And for 3 dimensions, you won't have a cubic differential here. You will still have the second derivative, but you will only repeat this for the other coordinates like this. So it will be square still, even if you have 3, 4, 5, 10 dimensions. Okay, so it doesn't depend on the dimension. Okay, so let's go to the diffusion equation with decay. Decay is very important. So decay is modeling, can model many types of phenomena. For example, chemical breakdown, spontaneously breaking down, or they are participating in some reaction with some other chemicals, or they are being absorbed by some cell, for example, in the medium. So the decay equation is like this: the rate which the concentration varies is proportional to the concentration, and it is negative. And this coupling constant here, the proportionality constant, we call the decay coefficient. Okay. So this is very, very general. You will see this type of equation in radioactive decay, epidemic models, the composition of materials, chemical reactions, etc. And if you solve this equation, it is very, very simple. You will get an exponential as a result, as a solution. And in the argument of the exponential, you will get this 1 over gamma. You will get e to the t minus t over gamma. So 1 over gamma times t. So 1 over gamma is a characteristic time. And this characteristic time, we call it equilibration time, which is basically a characteristic time it takes for the field to settle down when decaying, okay? Here on the right, I have an example, and it's a little exercise for you. So here we have some chemical reaction happening. For example, chemical A is generating probably chemical B, which is in a chemical equilibrium, chemical C, for example. Which one of those chemicals would you say it is decaying? And which one is not? So this is the exercise. You can type in the chat what you think. Chemical A is this one. Chemical B is this one with a peak. And chemical C just grows monotonically. A is decaying. A and B decaying. A and B decaying, Barrett. Why?
B decays after it reaches saturation, I believe.
And does it decay before that?
No, it doesn't.
Really?
Well, it's going up all the way. So I'm believing that once it reaches saturation, something is happening to the molecules and its concentration is decreasing. I'm not sure if it's decay, but yeah. But it is decreasing over time, yeah, after it reaches saturation. Not sure why. While C is not decaying for sure. It just reaches saturation as stayed at that point.
Sharon, this is not the argument, because in the 2D case, this surface would be a counter, would be a 1D shape. So this is not the justification. So yes, Barrett, you are right. Okay. Barrett, you are right. You're almost completely right. So first thing, yes, A is decaying. Second thing, yes, B is decaying as well. Where B is decaying? B is decaying all the time. Once B exists, B is decaying. B is decaying on the initial part as well, but you don't notice it going down because there's also a synthesis. So we have synthesis and decay, but it is decaying. You only see the decay as a curve, let's say, once it passed the peak, the maximum value. So it is, you can say it is decaying all the time, generating C, and then it stops decaying only when it reaches the equilibrium with C. Okay. And if you compose the two equations, so you have the diffusion equation and the decay, you just need to sum both. That's what you need to do. You just need to sum both terms, okay? Because both the Laplacian and the decay are proportional to the time derivative. So you just need to add them in the same equation. Now let's see the diffusion into a tissue, but this tissue is somehow making this field decay. So this tissue is absorbing, consuming, it's doing something to this tissue, and this tissue is making the field decay. In this situation, what you get is a exponential decay from the interface inside the blob of cells, or let's say the tumor. So you can have a tumor, a blob of cells composing a tumor, and as you go inside the tumor, you will see less and less nutrients, for example. So you have exponential decay in the space, okay, as you go in the tumor. And you can also solve the diffusion equation for a simple case and find that this typical length, this typical penetration depth for, let's say, for your nutrient will be the square root of the diffusion coefficient, okay, over the gamma, which is the decay coefficient. I can demonstrate this later if you want, but only if we have enough time, okay? So this effect also dictates, for example, the distance between capillaries, because you have, for example, a capillary here, and the field between the capillary will decay, but it cannot reach a minimum below what the cells need to survive. So you need to set capillaries close enough so the fields decay and not kill the cells between capillaries. So and also cell differentiation. For example, you have the embryo, and the embryo is absorbing nutrients. Naturally, the cells inside will receive less nutrients than the cells outside. So you can have some spontaneous differentiation because of that. And here I got some experimental data measured in a spheroid, a cellular spheroid, multicellular spheroid they call, and you can see the exponential decay, and you can also see that the field starts decaying before entering the tissue. Okay, so this is a nice effect. When you set your field below the diffusion constant line, you will see the global decay constant. You already saw it, okay? So this is where you change the decay constant globally, not for specific cell types, okay? So this is the exercise. I think I can give you guys some time to do it. Yes, I will give you five minutes to do. You just need to do the first one. You just need to grab that simulation that we built on the last lecture, for example, and set a decay and see what happens to the field. And also remember, you can take the exercise, the completed exercise in the students' materials demos. Okay, so this is the 2, 3, 2, and you can get the exercise done there. Okay, I'll actually do it while you. Let's quickly. Take your time. Okay, need more time. Fine. I grab the completed exercise. It is different. This completed exercise in the drive is different because it takes too long to achieve the exponential decay. So I started as the linear gradient, and this is you can easily see how from the linear gradient, because you have decay, you'll see the transformation between the linear to the exponential. Okay, and then you just play with the constants, right? Now, do you guys need help? There are two people that need more time. Okay, so now the graph resembles the heat map. Okay, so the second part is like this. You have a proportionality between time, the diffusion time, and the length of the diffusion. Okay, but there's also another time. There is the equilibration time from gamma. So 1 over gamma is an equilibration time. If we increase gamma, we make the field go down faster, okay? But if we set the diffusion coefficient higher, it will make the diffusion be faster, not the equilibration, not the decrease of the field. So those two coefficients do different things, and you can actually control diffusion time and equilibration time separately from one another. For example, let me show you what happens when I increase the diffusion. I mean, sorry, when I increase the decay coefficient. So I'm going here on the diffusion solver FE, steppables onto edit. Now about on line 38 on global decay constant, I will increase this decay. I will put it very, very high. So for example, 0.1. This is very, very high decay because it happens each Monte Carlo step. So I change to 0.1. Now I save the simulation. I will go back to the player and run again. Now you will see that the field settles down much, much faster. So look at the difference. This is 0.1. Okay, so this is the equilibration time. And this is 0.001, which happens much, much slower. Look, okay? But the diffusion time is different. The diffusion time is, imagine you have a drop of dye over here at x equals 0. How much time will it take to diffuse across a certain length? It's another type of time, okay? And you can control those separately. Generally, when you are building a model, for example, a tumor model, time is strange because you also have the growth, the cell growth. So the cell growth also parameterize time. Generally, you will see in the avascular tumor model that a much more important parameter is the diffusion length. So what would be the diffusion length in this case? So I will get back to the 0.1 just to show you the exponential profile. So the diffusion length here, look here at the exponential time. Let's see the half-life in terms of field. So the field seems to drop. It's dropping very, very fast, actually. So I don't know. You would fit this field profile here, but you can say, for example, that in 20 pixels you have no field. Okay, so you will say, for example, that your field penetrates at maximum 20 pixels. Okay, so this would be your typical length around that. Okay, does someone need help? I will move on then.
Pedro, one thing you might want to do is show them how to edit the diffusion constant and decay constant in the steppable while it's running. Don't
Oh, yes,
do it.
sure.
Don't do it and put it. Use the model edit.
So here in the CC3D user interface, you have in the model editor, which is this window on the left, steppable option here. So I click it, I opened the steppable menu. And then I open diffusion solver, diffusion field, sorry. And then we have the diffusion data and the boundary conditions in this menu. Open everything. And inside here, you can change everything. So for example, you can increase your global diffusion coefficient, let's say 10, and run.
You have to hit enter.
Okay, so now it works. Thank you.
And there's one other annoyance there, which is that if it's specified as an integer, you have to enter an integer. If it's specified as a float, you have to specify it as a float. So if you see the number is 1, you can only type 2, 5, 10, 50. If you see the number is 1.0, then you can have to type 1.2, 1.5. The decimal point does matter, so you have to remember that.
Janfid, I don't know if you can. I mean, if you rescale your simulation 2 times larger or 2 times smaller, for example, In your case, the pixel 2 times smaller would be like, I am rescaling my simulation 2 times bigger. Yes, you would have to rescale your diffusion coefficient as well. 4 times.
If we don't change the time scale, like let's say we imagine, I mean, we considered one Monte Carlo step as 1 minute. Then if we don't change that, then the decay constant wouldn't be changed, right?
Yes, yes. The
Because
problem
it
is
depends
that
on
when
the
you
time.
Sorry?
Because the unit of the decay constant is not dependent on the location.
Yes, in this case, not dependent on the location, yes. But you will have many cells with different diffusion coefficients.
Yeah, if we make it kind of 2 times smaller, then it would be the diffusion coefficient would be 4 times faster. I wanted to make sure.
Yes, probably, yes. Yes. But remember that rescaling, it's very complicated. In my simulations, for example, I resize everything and then stops working. So you have to, and even if you rescale properly, for example, you increase the area, then you reduce the contact energy, you do many in detail, everything rescaled. You even if you do this, you will have different behaviors because the lattice itself affects very much the detail. If you have more pixels, you have more detail, you have different fluctuations. But for the field itself, since the field runs in another lattice, not the cell lattice, yes, I think you are right.
Yeah, I just considered the diffusion coefficient, not the other parameters. Yeah, I know it could be complicated. Thank you.
Okay. So notice when I change the global diffusion coefficient, I get a different profile, exponential profile, because the higher diffusion allows the field to spread out better. Okay, so I will have a different profile for my exponential. Okay, and if I reduce my decay coefficient, I will get, sorry, I'm going too fast again. So I am changing the global diffusion and the global decay coefficients inside the model editor still, okay? So you hit pause, click on the value, change it. For example, I'll change it back to 1, for example, press enter, and then hit play again. So you'll see that you get another profile. Also, there is something that you probably noticed happens, which is when you change the global diffusion coefficient above 1, 10, 100, seems like the steps are going slower. They are going slower. And let's put 100 here. Look. The steps are going a little bit slower, and that's because for a higher diffusion coefficient, the solver will need more computation to solve the details. Okay. So I went through the solution, but I will show you on the code where you will need to change. So in line 37, 38, you have the global diffusion coefficient and the global decay constant. And also in the solved exercise, I started the initial condition from the linear gradient. This is very interesting because then you can see how it changes from from the linear gradient to the exponential, okay? And if I set the decay to 0, I should get the linear back, right? So it should be float here. Ah, no. What did they do? No, it's right. Okay. Diffusion data. Now global decay to 0. Enter and run. So now I will get back the linear gradient, but it will take long. So let's say if I increase my global diffusion here, it should take less. But it will still take time. So let's move forward, okay? Membranes and other types of cells, barriers, will have an effect on fields. So I just remember, you can block, you can bind, and you can absorb. So there are many biological processes that can make fields diffuse differently from medium to medium, okay? And we will test this with a membrane. So in the case you have a membrane and the field is trying to diffuse from one side to the other, because this membrane has a lower diffusion coefficient, you expect that the field diffuses slower inside this membrane. So you will have this step, this break. The line will break. You have a discontinuity on the derivative in the boundaries between the medium and the membrane. Okay. And to do this type of thing, you need to set a different diffusion coefficient for different cell types. So the diffusion of the cell that compose the membrane has to be different from the diffusion coefficient to the rest, to the medium, for example, okay? And then we are gonna create as an exercise this membrane and see what happens. And if you find it too easy, again, there is a challenge for you, which is basically the same exercise, but you have two types of cells to build the membrane. Let me show you. And there are two types of configurations here in which you can combine two materials to build a membrane. One, you put two layers side by side, and the other, you build blocks, one block over the other, alternating the material. And basically the question is, in which configuration, given that the diffusion constants are different for those two types of materials, which configuration blocks more the passage of the field, which one allows more the passage of the field, okay? And then build a simulation to prove your hypothesis, okay? This is a very simple mathematical problem. But I will do the exercise. If it's too easy for you, do the... I will just see what Jafid asked. Do you know how the solver discretized the domain for solving the PD for diffusion fields? Does it use the same mesh as we have? Yes, it uses, okay? Or does it generate smaller mesh? No, it doesn't. I don't know if you can do it. I don't know if you can solve the field in a more thinner lattice, okay? So this is the exercise. I will build a new simulation from scratch, okay? Basically what we need to do is set proper boundary conditions and build this barrier, okay? Which is gonna be frozen cells. So let's go. I will first close here. And in the XML, so go to your XML, hit CC3D project and build a new project. So I will name it membrane underline, just to make sure I don't have another membrane simulation. And I hit next. Okay. In the general simulation properties in the simulation wizard, I recommend reducing the lattice dimension. I would reduce a lot, but since I'm sticking to the original exercise, let's reduce to 200. Okay. And then we are gonna build the membrane in the middle, so in the 100 dimension coordinate, x coordinate. Also remember that you can get the done exercise in the material students materials. Okay. Leave the rest as it is. So 200 200 for lattice dimension. Next. So in the cell type specification, so let me catch in the slides here. In the cell type specification, add a cell type membrane and check freeze. Okay, we want it to be a freeze cell, frozen cell, and add the cell. So your cell type specification should be similar to mine here. So again, I type it here, the field name, I hit freeze, and then I hit add. And I want to know if you guys have your cell specification like mine. Okay, it is very simple indeed. Next, chemical fields. So we're gonna choose a field. Let's put oxygen again, because I don't know, it's useful, right? Oxygen. Choose diffusion solver. It is nice to use diffusion solver here instead of the the steady state one, because you can see the derivative inside the membrane changing. It is very nice. And add. Okay, so if you are having trouble with the exercise, please, you can unmute and talk. I will move forward, okay? If you have a problem, please tell us. The next, no need for...
Sorry. The diffusion solver FA select.
Yes, yes,
Okay. Thanks.
FP, yes. And then next, finish. We don't need the rest, okay? Okay, open your codes in the XML. Then go to the initial, to the uniform initializer, and there we are gonna set our membrane. So add it in line 73, uniform initializer, okay? Change the box minimum for X and Y to 45 on X and 0 on Y. So our membrane should go from 0 to maximum, okay? Okay. And then put the maximum. So I done a mistake. I didn't notice in the slides it was 200 for the dimension, and here is 100 for the size, the maximum membrane. So if you set 200 as me, put 200 on the uniform initializer as the maximum for y coordinate. Okay. And 55. 55, 45 to 55 in the x coordinate. Okay. The width you can leave as it is. That's just it. Oh, yes, sure. 95 to 105 is much better. It's more symmetrical. Oh, mistake here. Thank you, Caleb. Okay, now you need to go to your diffusion solver steppables, okay, and change the global diffusion constant to 1, line 38, and change your global decay constant to 0. So I will put 0.0110 because James advised that problem in the in the module menu. And also in your boundary conditions, set the proper boundary conditions, which are 10 and 0 for x, and or 0 constant derivative, or periodic. You choose. I will set periodic because it's the simpler. Okay. I will relaunch the poll. Then 0 for x coordinate, periodic for y coordinate. Okay. Remember that boundary conditions are always messed up. Okay. Now notice before you run, notice there are some other specifications. Okay. So for example, there is a secretion in cell membrane, in membrane cells, set to 0.1 in line 50. We don't want that. Okay. So comment it, line 50. Comment the secretion part, or set it to 0 as well. Also works. Okay. And then in line 43, okay, after global diffusion constant and global decay constant, you have the diffusion coefficient and decay coefficient for different cell types. So here is where you find the specific diffusion and decay coefficients for each cell type. So for cell type membrane, you can choose a diffusion coefficient lower. So if we set 1 to global, you can leave 0.1 for membrane. You will see the effect. And the decay coefficient, we want to set to 0, since we're not worried about decay now in this particular exercise. Okay, so lower diffusion coefficient for cell membrane and 0 decay and 0 secretion. Okay, I will move on. If you have if you're having problems, please unmute and talk to us. Now run the simulation. And you should hopefully see the membrane. Then same stuff, you can go to this box here and select the oxygen field instead of the cell field to visualize in the graphics window. Okay, so hit that. Then you can see the field oxygen diffusing. Okay. Are you here? I will increase the diffusion field because it will take too long for the field to settle down. So I will increase, let's say, to 10. Okay. Then you can see that the membrane is blocking the field. So now the field is penetrating the membrane with a lower diffusion constant. So this is a semi-permeable membrane, something like that. And once the field diffuses to the other side, it will start spreading fast again, but not inside the membrane, okay? And obviously, if you set the diffusion coefficient in the membrane to 0, it will be a wall, okay, a perfect wall. The field will not cross the membrane. And if you set to the same as the medium coefficient, it will be transparent. Okay, the field will simply cross. Okay, so someone needs help. In line invalid token. So does someone, probably a breakout room will be needed, don't know. Okay, guys. So in the materials, the student materials, I actually start with a linear gradient. It's very interesting, and then you can see the formation of that derivative inside the membrane. So hopefully I will have time to show you this in the end of the lecture. Okay. Okay. Now we want to open the channel and see what happens. Okay, so how do we open the channel? Do open a hole in the membrane to allow the field to pass? How do we do this? So let me get back to the code. Stop here. Get back to the code. And we will need two regions to define our membrane, because it will be like two pieces, right? The whole is actually two membranes, one over the other in two pieces. So how do we do this? First, very simple. You simply stop, let's say 90. So the middle is on 100. So you put the middle minus, let's say 10. And in the case of the upper part of the membrane, you set the middle, it is 100 plus 10. So you will have a hole which is 20 pixels wide. And save. Are you with me? So what did I do? I copied the piece of code region to region. Okay. Exactly the same syntax, but then I generate the first membrane from 0 to 90 in the y coordinate, and from 110 to 200, the other piece of the membrane. Okay, so what happens when we run? It bugs, it crashes, obviously. Sometimes it don't. Okay. So because I am a little bit of an anxious person, I will increase the decay to 10. Enter and play. And hopefully we will get some interesting effects. Okay, so you can notice that the field passes through the hole, and the hole affects the field way back. So if I pause here, you can see that there is this curvature on the ISO surface, and the field slowly walks through the hole. And way back here, you can see that the hole is already affecting the field. And if you wait a little bit, you'll get some nice images. Some more field arts actually. And also you will have somewhat the behavior of the membrane with a different derivative, but the derivative will not be will be analytical. This is what I mean. Is there a better way to set up the cells in the alternating pattern within XML without having to regions and without generating a PIF? So you can do this way here. So let me show you. There is this way, which is you select like this, and you do like this. Okay, so many regions. Okay, if you don't want to commit this international crime, you will have to generate in the steppables, in the start function. You can specify your initial condition. You can basically paint your lattice in the start function here. Okay, I can show you later. This is not, I don't intend to do this on this lecture because it takes time, but I am happy to know that someone is doing the challenge actually. Very nice. Okay, let's jump to the, oh no. First I need to know if you guys could reproduce. I don't know if I am redundantly relaunching the poll, but it's better to mistake up. Okay, need more time. Okay. Yes, yeah. Very nice. I see. Icy or easy?
May?
Is it?
Is it icy or easy?
It's Izzy.
Easy. Okay.
Yeah.
Easy. I will check if you could do the challenge after. I hope everyone could finish the exercise. Now I will talk a little bit about the diffusion equation with sources and sinks. This is very, very important for tomorrow's lecture, that I need more time in the next lecture, the avascular tumor simulation, because it can be it can take quite a bit of time to build the avascular tumor. Okay, so I will talk about the diffusion equation sources and sinks today. Okay, so basically, what is source and sink in biologically speaking? So sources and sinks, biologically speaking, are, for example, if you cut yourself and you start bleeding, this is a sinking, let's say. So if your blood is the field, and if you cut yourself, you will start sinking field, for example. Okay, so when you take a shower, that I really recommend you to do, the shower, when you turn on when you allow the water to flow. The shower can be thought as a source of water, and the sink can be thought as a sink. Okay. And also when you drop, for example, a drop of dye on the water with your pipette, this also can be thought the moment when you drop the drop, you can thought it as a source as well. Okay. So mathematically speaking, source is basically summing another term in the diffusion equation. So for example, if you ignore the Laplacian here, the d Laplacian c term here in the middle, you will only have what? The derivative of the field, which means how much the field changes in time, equals to s. So this is very, very simple. If s equals 1, the field grows by 1 each Monte Carlo step. That's it. Okay? The thing is, you can specify s as a function of the space. So you can set, for example, in the omega region, an s, a positive s, constant s, but 0 everywhere else. So in this case, you have, for example, your one cell secreting, another cell secretes less, other cell secretes more, etc. Okay? Or the medium secretes and the cell doesn't. You can set all those types of things. Obviously, if you write minus s, it will behave as sink. Okay? The problem with minus s is that your field can become negative. Okay, because your rate of change is always negative. So you can go negative. There is no limit. What is the opposite? It's upper limit and down limits? I don't remember, sorry. You don't have a limit for, sorry?
Lower limit.
Lower limit, okay, thank you. These are things that I know actually, but I always stall some words. Okay, and you can also specify source with decay in the same region of space. So what happens when you do this? What happens when you specify a source and a decay for your field in the same region? What happens is that your field tends to an equilibrium value that will be different from 0. So if you have no source, only decay, your field tends to 0. It decays, and goes to 0. If you have a source, an input, a flow, a flux, a positive flux of your field, what happens is that they fight each other, and then they reach an equilibrium different of 0. So I will demonstrate that to you because this is my last slide and I still have some minutes, okay? Hayden said 20 minutes 2 minutes ago. So I have 18 minutes left. So I will demonstrate this to you. And hopefully you like those mathematical demonstrations. This is what is left. Okay, so let's start with the diffusion equation. So the derivative in time, okay, equals what? The diffusion coefficient, the Laplacian of the concentration, okay, plus S and minus gamma C. Guys, since we have time, help me. What do I do here? What do I do here? What's my next step? Please. Maybe Chafit can help me. Easy? Can you help me? How do I solve this equation here to get the result on the slide? The maximum, the equilibrium value for concentration. Barrett? Someone, please.
Set it equal to 0.
Make it 0 here?
Yeah. Then the rate
Why?
of change of your concentration is 0
But why?
because you want the maximum concentration.
What does it have to do to derivative 0?
That's the equilibrium phase, right? When you have equilibrium, your concentration isn't changing with time, so it should become 0.
Perfectly. Yes. Very nice. So you both got right. Sorry, I am too boring. I know boring is not probably not the right word. It's okay. So I'm left with this. What can I do now?
You have a oh actually no you don't worry.
What can you do? Sorry?
No, it's all right. I was gonna say you have a quadratic, but it's a second differential, not on the C.
Yeah, the problem is
What
this
do you
guy
wanna do?
here. Sorry?
Well, you can expand your gradient, your grade function out.
Okay, so I will give the answer. Sorry, I will give the answer because we have to move a little bit faster than this. So let's think of a special situation. We need to get rid of this term. Let's think of a special situation. So let's say I start with my field 0. So my field is down here, okay? And I have periodic conditions to y and x, okay? So if I set this special situation here, my field will always be flat. Always. If my field is always flat, the Laplacian is always 0 because the Laplacian is what? Laplacian greater than 0 means this. Okay, so you would have like a peak here. Laplacian less than 0 means the opposite. So you have a valley. And Laplacian equals 0 is everything that is like a plane. Okay, it can be an inclined plane, but it must be flat. So if I set periodic condition, it will always be flat. So this is always 0. And I am left with the most simple. Is already the steady state C. Okay. So this will be the steady state. So no. That's it. Okay. Now I will really quick demonstrate one more for you. I will demonstrate the length, the typical length. I showed you that the typical length is when you have the cells here in the tumor, for example, and the field is here, and starts decaying and goes to 0. Okay. How can I get this guy here? So let's go to the diffusion equation again. So time derivative equals the Laplacian, beautiful, minus gamma c. We don't have secretion. So I want the steady state here again. So 0 equals the Laplacian minus gamma c. Okay, what is left? How can I get rid of this term? I cannot get rid of this term because this is curved. This has curves. Curves, Laplacian not equal to 0. So this stays on the equation. But what I can do is model a simple case again So let's say I have an interface and I know that the profile of my concentration field is an exponential. So I will suppose that my solution is an exponential. So C equals E to the minus, let's say, X over L. I will suppose this. This is an ansatz. And sets, is it like this? Don't remember. Which is a good idea for the solution. Okay, this is an ansatz. So let's plug this in the equation. So I also limited to a one-dimensional situation, or you could think this as a blob of cells, and instead of X, you were talking about R, the radius, okay? From outside to inside, okay? So when we plug these ansatz into the equation, you will make the differentiate 2 times in relation to the spatial coordinate here, and you will get 1 over L squared E to the minus X over L times D. So this becomes this. And then minus gamma what? Minus gamma E minus X over L equals 0. So because equals 0, dies, exponential dies. Now you are left with 1 over L squared and na. Then na. That's it. Okay? Very simple stuff again. So why did I put an ansatz like this and not like this constant times the, well, simply because the constant is arbitrary. This is not arbitrary. This depends on the parameters of the equation. The number I multiply here outside the function, this is arbitrary. Okay, I could also put another exponential, be the most general form, right? With negative here, positive here. But just for the sake of achieving the relation between the L and D and gamma, you suppose a simple solution, an exponential, decaying exponential here, and then you find what is the relationship between the parameters, because this relationship between the parameters should apply to this simple case. So you can use the simple case to get a simple relation. Okay, so that's it. So I'm finished. We are left with 10 minutes, and we will have questions and answers now. Oh, sorry. I need to run the... Oh, next lecture, we are gonna see secretion and absorption. So hopefully we will make at least one of those simulations here that I'm showing you, which is basically secretion and absorption, okay, with cells. For example, one cell secreting, other absorbing, and secreting and absorbing depending on the configuration of the system as well. Okay, so I hope I see you guys tomorrow, and that's it for today. Thank you very much.
Before you go, please fill out the poll.
I do have a question here, Pedro. Will you explain ansatz again? I think since we have a little bit of time, we could probably do that.
Sure. So an ansatz is just a clever idea for the solution. So you are trying to solve an equation, or you are trying to solve your problem in your life. So there is a solution, and you imagine, this solution must be like this, must have those properties, because I know this because I know this this system. I know how it behaves, then I know more or less how the solution should be. So in the case of chemicals outside, and then inside they start decaying towards the center of the tumor, let's say, a good idea for the solution is to say that it is something like an exponential. Okay, so when you you take this solution, this supposition, and you plug into the equation and see what happens. What you come out with, okay? This is the idea. So ansatz is a clever idea for your solution. And then you take this idea and you test in the equation you have. I'm thinking about a practical example. So it's like this. You are trying to cook a new food, but you are cooking this food only knowing the result. You know more or less how it should taste, how it should be, but you don't know exactly how to cook this food, how to solve the problem actually. What do? You suppose, well, I know it looks fried, so I will fry. It looks like the guy put some I don't know, some seasoning. So I remember the smell, so I will put this, and that. So you are basically cooking by ansatz. You know how the solution should be, and then you start solving from the solution itself. And then you discover then the solution is actually a different solution. Okay, so this process many times will be repeated over and over. So in this very, very simple case, with this very simple ansatz, we got the answer already. But in a more complex situation, you will try one ansatz, it will go wrong. You try another one, you basically play with it. Yes, Itamar got right.
Just another reminder to please fill out the poll while it's still active. Then we'll have some open question and answer time for anything that we talked about today.
I have a question. It has to do with the scalar fields that we started talking about today, either with gradients and things. And so I'm working on a model that's working on like essentially cells having like their own oscillators and the synchronization of their interior oscillators. And essentially it's a kind of a cosmetic thing. So could I share my screen really quick?
Sure.
Okay, thank you. Oh, it says, okay.
Yeah, Pedro, if you wouldn't mind unsharing. There we go.
Oh, thank you. Okay. So can you see it okay? I don't know what you can see.
Yes, we're seeing your CompuCell player.
Awesome. So basically I was wondering if there's a way to, because I have one of the scalar fields up right now for the cells, but I was wondering if there's a way to make sure the medium stays black, or essentially so the medium isn't affected by the field. Because if we go back to like the cell fields, I have to keep running it. Oh, no. Well, if you run it again, like in the cell field, the medium's black, which is like what I'd ideally want, because as soon as I change it to the new scalar field that I applied in the steppable Python file, it now turns green. And so I didn't know if there's a way to make sure the medium cell type is not, it doesn't have the scalar field applied to it. Does my question make sense?
Yeah.
So you want to exclude the chemical from the medium?
Ideally, yes. The weird thing though is that there isn't a yes. Yeah, that's what
So
I'd
you're
want to
saying
do.
that the chemical, so what are you trying to do? You're trying to show what?
I am trying to
You
show
want to know the
essentially,
concentration of a chemical inside your cell?
I'm showing, so not necessarily chemicals. This is based off of essentially you looking at if each cell here has its own oscillation. So there isn't necessarily a chemical that's applied. More so the scalar field is used to show the oscillatory value.
Right. That's a standard thing. So you use a tracking field.
Yes.
And if you use a tracking field, then you should be able, then you can have the background should be, I understand what the issue is. You're saying that the value is green instead of black, and that's because of the scaling you're using. 0 is green.
Okay. So
Numbers are going between -1 and 1, and you've got green as 0.
yes.
So the values are 0 in the medium.
Mm-hmm. Which is good, but I guess is there a way to exclude the medium from this scalar field altogether, this tracker?
No, you can't do that.
Okay.
It's going to give a 0 value, not a null value.
Oh, okay. Okay, that makes sense. That makes sense.
It's a good question. It's a reasonable thing because in fact there is no value in those pixels, but it's assigning as non-value to 0 rather than not a number.
Okay,
That's something
that makes sense.
that's something you could put as a pull request as an option. It would be a reasonable thing to do.
Okay.
Yeah.
Thank-
If there could be a way to have it override the medium color so that it's always black, so you get nicer pictures would be good.
But she
But
can do, she
if-
can do this.
Sorry.
How would she do it?
You can create fields in the Python file, so you get the field values for each pixel. Then if the pixel is medium, you set to 0.
Right, but that's a slow thing to do. She's using a tracking field, I think. And so it's different from the diffusing field.
Yeah, but you can do it, let's say, one Monte Carlo step only to take a picture.
Oh, well, that's certainly possible. I mean, you could do a lot of post-processing if you like, but I don't think there's an option. If your values went between 0 and 1, then the medium would be black. But the way you've got it scaled here, it's not gonna. I don't think you can do it. TJ, do you know?
Let me make sure I'm clear on this. So the question is to have specific subdomains in the space be rendered as black instead. Is that right?
Yeah.
No, currently it's not. And the reason is because all of the field values are just blindly mapped to the color scaling as depicted in the color bar on the left. And currently there are no features to discriminate between which voxels are mapped to the color bar and which are not.
Okay.
I don't think it would be too much work to implement that functionality. So yeah, if you wanted to create an issue on the GitHub repository, we could certainly look into that. It would certainly be useful for a number of applications.
Okay. Yeah. Okay, yeah, definitely. I will look into that. Thank you. Thank you so much for all of your input. I really appreciate it. Yes, thank you.